I've got two notebooks that I'm going to go through here. They're toy notebooks, real world use case, but they're examples of how I think you can make the most out of Argilla's image field, which we've recently finished. I made these notebooks while we were building it to try it out. The first notebook is about fine-tuning a model for image search. It's not a full search engine, it's just a training notebook. Takes a toy data set from the hub and pushes that data set to Argilla, and then uses sentence transformers to model. It's all contained in this notebook. So we'll just connect to our Argilla instance. I've got a template space running. Here we've got a settings definition. This is the main change in this release. We can now define something other than a text field, right? The last year, the only thing we've had is a text field, but now we have an image field, and it works a lot. A text field has a name and a title, and it doesn't have any other parameters at that settings level. Then you can create that data set and create questions. This is a search similarity task. So we want to know whether a piece of text is similar to an image. We're going to ask the annotator, does this image match the query? The query is a piece of text and the image is the image. And they can say yes or no. It's just a binary question. We can load that data set, this toy data set that I've made of image search queries, and we can log it to Argilla. We're improving this in the next release, but we need to cast our label column in this case because it's a string to a string value. This is the data set we're working with. It's a column called image that contains URLs that point to an image file, a JPEG. So you could just copy that out. It's a public URL. Should be a public URL. Maybe I cropped it too much. That's one image, and they're all publicly available, right? So Argilla works with these public URLs. If you push a record with a public URL in, it will leave that and store that on the Argilla database. But if you load a record as a PIL object, then it will byte64 encode that PIL image and then push that to the server for you. When it comes back, it will decode it as a PIL object. We're not using that feature in this example, but that's quite cool because datasets also encode as PIL objects. It means that when we log a dataset to records.log, it'll be compatible. You can just leave the image column as it is. You can just pass the PIL object. The next thing is the query column, which is just a set of search queries. These are actually synthetically generated using a VLLM, and they relate to the image or they do not relate to the image, and that's what the label says. We could have a little inspection there, or we can wait. You'd see that this query here should relate to this image, and this query here should not relate to that image. Okay. Then we're going to train our document retrieval model, which is a similarity model, right? And we're going to use the package sentence transformer and get the clip vit B32 model, which isn't the most state-of-the-art model. There are some improvements. There's some ColPali-based models I'll show in the next notebook. But clip's small, and we can train it in a notebook like this, so it's quite a nice example. And we'll say that we want to use cosine similarity loss between the text and the image. Sentence transformers has recently been completely refactored. It's now much more like transformers, which is cool. It has training arguments and a trainer and this sort of API interface. And we can pass this data set straight into sentence transformers. So that's the notebook. It's just a really short trainer. And I'll share with you now what that looks like in Argilla. Cool. So in Argilla, what you get is the same representation that you saw in the data set, right? Your search query, the image rendered like this, and the records. You can see that the suggestions from that column have been passed into the label value. And that's it. This is a similarity task. Is the query similar to the image?
You would also be able to do some vectors attached to the model based on the clip embedding.
What kind of use cases could you apply that to? You could apply that to, a search use case or an image similarity use case. You could use it to collect queries about images or to collect captions about images. There's a number of different use cases. It's quite an extensible model, just a similarity model. Okay.
Maybe you can fix the issue, or are you okay?
Yeah, go ahead. I think it's the notebook's out of memory, so I need to restart. If you go first.
Share a cool new feature on the Hub that was released today. We have this new SQL integration for Hub datasets. Whenever you go to an arbitrary dataset on the Hub, that there's this underlying API that indexes all of the documents and information. You can use that API now to do basic text search. Getting an unexpected API are a lot of issues today, but normally you would be able to do basic text search. And the cool thing now is that what we launched earlier today is actually the SQL console on top of that. So basically within each individual document or each individual data set that you have hosted on the Hub, you can basically write SQL queries. And now my SQL queries aren't very up to date and on point, but what I created today was this text to SQL Hub dataset thing. So whenever you would select a dataset, then you end up visualizing this dataset. Based on this visualization, you can get an idea of the columns within your dataset, the input and the output text. Underlying, what I do is get the dataset definition from the Hugging Face API and then forward that to the Hugging Face inference API, which you can use for free to call LLM models. This is rate limited, but you can still have these models available for free to experiment a bit. And this is what I do under the hood. You can actually write your SQL queries. There's this console that you can open up. You can define your SQL queries, but as mentioned, my SQL capabilities are a bit rusty. So what you can do is write natural language queries there. Maybe you would want to have the average length for each prompt based on the act. So let's write that down, average length for each prompt grouped by the act. And then under the hood, this information along with the dataset definition is forwarded to like this LLM in the background, the inference API that I referenced. And then when you would query the dataset, you actually end up having this definition here. So the SQL query that's supposed to be generated, you can actually run this query. Based on this, you can directly from the Hub, directly from the datasets viewer, you have all of these analytical capabilities available. This is a cool tool that I developed today to work with that. Under the hood, what you can see is actually this Hugging Face, let's see, inference client that you can use. So whenever you would want to do inference, you can actually install Hugging Face Hub, then import the inference client and your Hugging Face token to authenticate it, but it will not incur any costs. But based on this definition, you can actually use the like LLM chat completion methods for API calls. One example to find these models is you can actually go to models in Hugging Face. Then for these models, what you can do is go to other. You can choose the inference status. Frozen means that the model isn't available. Cold means that the model is maybe available, but still needs to be loaded into memory. And warm means that the model is actually available and loaded into memory. You can then select this specific inference status, go to tasks, for example, and based on that, select the task that you might want to cover. For text to image, you end up with these Flux models that are pretty cool and are getting a lot of attention. That's also one of the models that we'll cover in the notebook. Whenever you choose one of these models, let's go with the Snell one because it's quicker. You can then go here and you have this code to query the serverless inference API for free. Once again, it's rate limited, but you can use it out of the box. I will now go to the notebook that I prepared, and that's actually using this Flux model under the hood for generating an image preference dataset. So in this case, there's this concept of preference pairs for image generation, which is similar to whenever you would fine tune a normal LLM. And in this case, I'm using this Tom Group and Pixel Pros dataset with 16 million synthetically generated captions. Based on these captions, I will generate images. First, you need to deploy the Argilla server. You can follow like guides that we have publicly available, but basically it's some button clicks and then you will deploy your free instance of Argilla on the Hugging Face hub. On top of that, I will install Argilla sentence transformers. Initially, we'll be authenticating to Argilla. The URL is formatted like the name of your organization or your account in Hugging Face, and then also the space name. You would also need to provide an API key for the Hugging Face space. Whenever you work with a private space or your own data that you might not want to share with the world, you can use your Hugging Face token as authentication for accessing that space. So what I did here is actually used once again this dataset viewer. Not running. Oh, connect. So this dataset viewer, and within this dataset viewer, you can just do a vibe check. So not sure, it's not working. Let's call it demo issues. Normally, you can have this embedded iframe of the dataset. For now, I will go to the dataset URL directly. So just to have a general idea of what the dataset looks like and what kind of data is in there. So here, once again, you can see the ID, specific identifier. Then on top of that, you can see like a URL that's actually contains an image. And on top of that, there's some keys, statuses, a caption for that specific image, and the model used to generate that caption. We have a general idea of our data. It's important to think about what you want to do with your task, and that's what we think about when actually defining these Argilla settings. So in this case, we'll define our Argilla settings with a text field that should have the caption of the image, then an overview of the original image, an image that was automatically generated, and another image that was automatically generated. Based on the caption and the original image, some annotator might get a general idea and feel of what the image should look like. Then the model generations that came up. On top of that, we will be adding some questions that the annotator is supposed to answer. The annotator can choose between image 1 being okay or image 2 being okay, and provide some additional comments on why the image was good or bad. These are things that you can think about when defining your dataset. For the metadata, we'll be adding properties present within the dataset, like toxicity and identity attack score. Toxicity is about the toxicity of the image. Does it require parental guidance or these kind of things? Identity attack is about a personal image representation of within an image. On top of that, we will also be adding a vector field. In this case, we will not be generating the vector field with a clip model, as Ben is going to show later. We actually have text available. So given that this text semantically represents this image, we can actually use just the caption that. Whenever you have these settings, as a dataset name, you can create your dataset. And then based on that, you can start adding records. So in this case, we'll load the dataset with streaming enabled. This means that whenever you load the dataset, you just load the dataset definition and you don't load all of the content. So that might, whenever you load the dataset with other images, this will be a huge dataset size. For now, we'll just load a subset and include 25 examples. Then we'll, based on the rows, create a dataset list. And here you can see all of the, we can see that there's 25 images that we obtained. An image or a specific row looks like this with the URL. You have the nice thing about the URL is that this URL can directly be forwarded in Argilla. Normally, we transform a pill object to a data URI, which is a data representation for loading images into HTML. But this has limitations in terms of size. The nice thing is that you can use local images and you don't need an image server with public URLs. For this use case, we can just use the public URL that's available. Then whenever you go to the dataset, we did a check and noticed some of these public URLs weren't images. So just to filter out some of these initial bad examples, I just take common image extensions to filter the dataset based on that. Then we'll have the 18 rows left. In this case, we actually copy pasted this code from the Flux model that I just highlighted that you can use for free given your Hugging Face token. And based on that, we can actually send a query to the model, convert that text to an image. So in this case, the example of the code was astronauts riding a horse, and this works pretty decently. It's a nicely generated image. But then we need to scale this up to more images. What we'll do now is define this mapping function that will take input from the original Hugging Face dataset and access the columns that are available. In this case, we'll not be using batching because the Hugging Face inference endpoints are rate limited. So this causes the model to be overloaded, and then you can get the responses back from your images. Then we'll just loop over each individual entry within the dataset where we get the original caption, so the description of the image that's supposed to be generated, and forward that caption. For simplicity, we added a space to avoid caching and generating a new image. After running the code, you can see image 1 and image 2 that have been generated that are present within the dataset. Do note that these are pill objects, as shown here, because we convert these images to a pill representation like the Python package. We convert it to the storage like a data URI. And then we'll be adding vectors on top of the caption. We have this mapping function where we take the Hugging Face dataset, pass the function, and batch everything instead of an individual row dictionary containing a list of items. And this will actually get a list of all of the captions, convert them back to a NumPy representation. This NumPy representation of each one of these vectors needs to be converted to a list to be accepted by Argilla. And then we end up with this original caption vector, and we attach that to the dataset as well. Then whenever you go into the Argilla side of things, you can pass your entire Hugging Face dataset as records on top of the dataset setting definitions within Argilla that don't align with the dataset column names. We define a mapping. As we saw within the dataset, there was this ID component that we need to map instead of using the original caption column within the dataset. We'll map that to caption, and then finally the URL will be caption image original within Argilla. And then after running this code, you'll end up with your Argilla dataset, and you can start your annotation process. So that's how you would go about generating an image dataset. The part about image generation is useful for demoing for examples. And then whenever you would want to scale this generation, you might want to use your own model. You might want to use paid services to do the generation, either by Black Forest Labs themselves or through the Hugging Face API services. I'm not sure if there's any questions. Maybe Ben has some ideas about following up with the RAG overview.
Yeah, it flows together quite well. The next notebook I'm going to show is about RAG, so I can go into that when we're ready.
If you have no questions, feel free to continue.
The notebook that I started from was by a colleague at Hugging Face, Merv Nguyen. She shared last week this multimodal RAG using ColPali and Bialdi and Qwen VL. What you have here is a vision language model and a Colbert-based retrieval model. Colbert is a new form of sentence representation that can be used for search. It's really efficient, but also performant. And this version of the algorithm is based on another model called Pali Gemma, which is a multimodal Gemma model. It's a state-of-the-art representation of documents. It's supported here by Aldi. It's not fully integrated into Transformer, so it's a little bit difficult to use. And the Qwen VL vision language model, you can combine the two together to create an open source document retrieval or multimodal RAG system. This notebook Merv shares is really cool. It shows you how to apply this use case. I was just playing with this in the interim. One thing I thought it could have would be integration with Argilla. I set that up in this other notebook, but I might come back to this later on. In this example, I take the documents that the RAG application is using to answer the questions, and I push them into Argilla. It's a pretty small change. I still index all of the documents, but this time I use a custom data set that I created for document similarity. I got that from the doc VQA dataset, the document visual question answering dataset. And so I create just a small index of that. That's what's going on here. And I'm using Bialdi's multimodal RAG framework because that's one of the only frameworks that supports this ColPali model at the moment. It'll probably be integrated into frameworks like Llama Index or LangChain in the future. So I would really see this as quite an experimental notebook, but it's cool to try out these latest models. It requires Qwen 2 conditional generation and the image and text processor, which is in the latest release of Transformers. This also isn't in the version of Transformers that's on pip. So you'll have to, as the notebook shows, a custom version of Transformer and also Bialdi. Then you have a processor and a search index. We add all of our images from our dataset into our search index. This framework for RAG requires image path, so that's why I'm doing that there. Then I create this function that takes a query and an image, and it will answer the query about the image. I have to represent that as a chat conversation with a list of objects like this. And this is a custom representation. I have to process the inputs, move them to the GPU, generate some IDs, trim those IDs and decode them, and then return back the text. And that's what Merv does in her notebook. And so then I add on to that just Argilla integration. I do that by defining a data set with an image field now. I take the text that was in the data set and the answer that the model generated. I push that to Argilla. And similar to the sentence transformers optimization notebook I shared, I just add this binary question to say whether this is a match or not. I iterate over my data set. I run my function to get my answer, and I push that into my records, and then I log my records Argilla. And so what is this? A really small toy data set of questions, images, and answers. I think this is quite a cool use case for Argilla because it's really text centric, and it's something that Argilla probably could solve in the near future, and that you could definitely use Argilla for. Let's say a complex question like this: what is the total donation? You'd have to look through this document, scan this document. You'd get the answer here. The total donation is 94,000. We could combine this with a text question to take that answer. Or we could just say, okay, this answer isn't in the document. I could say, no, that answer isn't in the document. And I could use that to fine tune a smaller model or that ColPali that I'm using in the notebook. I'll just go back to the notebook to show you some other stuff in there. I'd recommend that you take this one and try it out. It's quite an experimental using these more obscure frameworks. What we have here is this RAG tool that has this ColPali model. If I go back to Merv's original notebook, what you see here is that I'm indexing just a PDF. I have a PDF document with multiple pages. So it's already loaded. And it looks like this, right? It's a paper on OCR and the future of OCR with multi-modal LLMs. So it's a relevant paper. And I can pass that to my RAG and it will index it. I can now search, maybe something more relevant would be, what is OCR 2.0? And what you'll find is that I get a document. I've said K here, so say K5, that means I get the top 5. I'm retrieving from that document the most relevant pages based on my search query. Now I'm combining that with the vision language model. I'm going to use those pages to answer the question. And that's the inference going on right now. OCR 2.0 is a type of optical character recognition technology that can recognize text from images or documents. It is an improvement from the original OCR technology. Okay, so it's a pretty basic answer. There's more to it than that, but it's clearly read the paper and it's used to do that. I'd recommend taking a look in these 3 notebooks. This first one by Merv, that's just a really nice little example of this document RAG use case on a paper. I've added Argilla into this and made it over multiple documents. You can set up a feedback task in Argilla over an application that does that. This image search fine tuning, which you could also follow on from those first two.
Cool, thanks, Ben. And all of the inference for these kind of things were just like running on a Google Colab GPU or the page.
Yeah, the ColPali stuff and the Qwen model is quite compute intensive. I struggled to fit both models into memory inside that notebook. I had to be quite conservative. That was what was happening when I had the error, that I just had the two models in memory and for too many images. So I'd say that notebook takes up a lot of memory, and it's more of like a exploration of some of the state-of-the-art models, not something production ready. But the image search fine-tuning with sentence transformers, that's one of the smaller models that you can get for multimodal tasks like that. It definitely runs on free tier Colab or probably higher end MacBook Pros, and something people can try out.
Cool. A little bit towards this with document notation or these kind of things. Do you think you can tell us about that? I know we discussed this earlier today.
Just started working on image field and released this in the last month or last few weeks. Obviously, the image annotation space is really populated. There's a lot of people annotating images for a long time. So the immediate question I think you ask yourself is, what can Argilla do here? What would make Argilla distinctive? I think documents jump out as something that take advantage of Argilla's extensible interface and these question answering tasks. We're working on ways of adding coordinates to Argilla as suggestions, so the user can see certain parts of the page and use that to help them answer those queries. We can bring together multiple modalities and they can use that for their feedback task.
Thanks for the clarification. You mentioned, or there was a question from Muhammad about how do you embed images? How does it generally work? Because there was some issue with the URL, so he joined late. How would you go about fine-tuning an image embedding model?
I'd recommend that you go to sentence transformers. There's a tutorial in their repo for Clip that's from the previous version of their API. So it's not ideal, but the explanation is good. And then you can take this notebook, which is re-implemented in the latest API. That will show you how to fine-tune a Clip model. So what's distinctive about Clip compared to an image embedding model is that it's an image and text model. So you can create a data set that has one column of text, one column of an image, and a third column of a label, typically a 0 or 1. The 0 says these images in text don't match, and 1 says they do match. You're training the sentence transformer to learn that images and text are different, and to create an embedding space that puts those representations far apart. But there are a number of different loss functions that you can use within sentence transformers. That depends on the data and the scale that you have. If you have a small data set and a limited amount of time, and you probably want to take advantage of rule-based systems to get a reasonable size data set together that you can review in Argilla, it's best to start from the cosine similarity loss and labels of 0, 1, ordinal labels, so that you can build up a representation of a use case. If you have more data, it can build up more complex representations, like more detailed scores. You could use other loss functions to train with more precision.
Thank you for the answer. I believe there was another question about PDFs, converting PDFs to images, and how does he process these PDFs for training and embedding models? For forwarding these images towards the model, you need to do some cropping because of these image models. You expect the images to be a similar size. Do you have any experience with that, or?
So typically you train image models in NumPy arrays, you'd encode those. But if you use the datasets package, a lot of that is taken care of for you. And so sentence transformers integrates with datasets. So you can define an image column and then use dataset features to say that it's an image in that column. That will be encoded for you in the sentence transformers framework. Another thing you mentioned, David, was augmenting and manipulating images. That's something that takes place in computer vision that basically create random edits of a given image to encourage the model to generalize. In this kind of task and at this sort of scale, it's probably not necessary. You would want to validate the performance of your embedding model on a number of use cases before you go for that, because the model's already been pre-trained and it probably generalizes quite well unless you're going to a very distinctive domain. But there are packages for ablations where you can create copies of images to help your model to generalize. There's a question here about how is an image embedding different from a clip model? An image embedding model compares purely image to image. It's a feature extractor like from ResNet, and there are a number of others for image similarity. The other part of that question is about ColPali, an image embedding model. I don't actually think ColPali is from Google. PaliGemma is from Google, and ColPali is a Colbert style PaliGemma model. I'd have to double check the author. I think it's in the notebook because I pull the model. Yeah, it's by a company called Vidor. Yeah. If you drop the link in there. Nice one. And they create that framework as well that Merv uses in that notebook.
Yeah, and I think for benchmarking your image embedding model or your clip model in your example, you would want to create, for example, a dataset in Argilla where you work on your specific use case, which might be RAG or maybe some other thing that relies on embeddings. And then you would go about labeling them by hand. Or you might use a bigger model to label the similarity or dissimilarity between these sentences and images, or images and images, or either one of these combinations. And then whenever your labeled data set, which can be like relatively small, you can go over this benchmarking. And whenever it underperforms, so let's say that 50% of the time you end up getting the right models from your vector search database, then you might consider using a better model or fine-tuning. Yeah, ideally you want to have a model that's as small as possible because it's cheaper, it's more efficient, but it also depends on your quality standards and service level agreements with your company. Then there was one final question from Richard, or did you want to ask a follow-up, Mohammed?
Hi, David. Hi, Ben. Can you guys hear me?
Yeah.
I wanted to understand more about how these image embedding things work. I couldn't really understand like how they work. You said something about a feature extraction for training these image embedding models. So, for example, I have an image. I feed that to an image embedding model, get an embedding, and then I'm feeding that embedding to a vision language model, right? That's how it works. So how does this interaction work? How does a vision language model understand those image embeddings? Are they trained in a sequence? How does that really work?
There are different architectures stretching back. Clip is one of the earlier ones where you have a visual representation that the model uses. More recently, there are models with multiple representations, like a language and a vision representation that are combined together. And then even more recently, there are combined spaces of vision and language that the model uses. The notebook that I shared uses two different models, right? The ColPali model for retrieval, and then the Qwen VL model for understanding the document and answering the question.
The retrieval is then done based on the embedding of either the search query or the image. Then it will go into your vector search database or any other database that you might have. Query gets the relevant images, and then based on the relevant images, forward those to the model. So not the embedding from the retrieval is directly forwarded to the following step, but the actual image, and then the actual image is handled by the VLM in this example.
And what seems to be settled now amongst VLMs is that there's a vision encoder into a single decoding space. So the vision encoder and the text encoder can be swapped out for the given input, and the same decoding space is used to understand that task.
Okay. And for example, if I'm training an image embedding model, you have an image, you have the text, and you have the label. So a 0 and 1. That makes sense. For an image embedding model, you said something about feature extraction. How do we train an image embedding model in that sense? How do we know that these features are enough to describe the image?
You probably don't need to go to that level of detail if you're looking to use an image embedding model. A transformer model can be used as a feature extractor by changing the way that we handle its output. We can take a sentence representation as opposed to a word representation from the transformer. We can do a similar thing with images, and that's what sentence transformer takes care of for you. So when you use clip and sentence transformers, it will take the averaged representation of the image and optimize that for your use case. So you don't need to use transformers and its feature extractor and to perform that multiplication or the averaging yourself, but you could do. And the reason to do that would be, let's say there was a vision language model that was particularly good and you wanted to use that in a way that it had never been used before. And the example of that is ColPali. That's what Vidor, the authors of that ColPali model, have done there to create that custom model. But in most use cases, we can work with existing models.
For example, if we have images, let's say images have plots, they have pictures, how do we encode their representations? Like
That's
a clip, like you have an image, you have the text corresponding to the image. This might be a repetition of the question. What if I have plots in the image, pictures in the image? How do we translate that?
all of these models are trained on like general data. So for most models, you can actually backtrack what training data was used for these models. I don't think most of these models are trained specifically on plots data or table data in an image format. So then you would probably go about fine-tuning your own model. In that case, you might think about what these models do under the hood or are supposed to do. They are supposed to give similar representations based on things you deem as similar outputs. You would take an image, look at the plot, think about what the plot represents or what the image represents, and then try to create an associated label or question for these more advanced models and create a data set based on these assumptions that you make for your image. And then you would iterate and fine-tune a model based on that. These larger models, due to the fact that they have a bigger world models under the hood, can do more than smaller sentence transformer models, because even for humans, plots data or table data isn't very well represented.
The training, the pre-training phase of the clip models is really similar to the fine-tuning phase that I showed, but uses a different loss. The model was trained to learn that a piece of text is similar to an image, and vice versa. So in the context of a plot, you might take a description of a plot and an image of a plot, and the model would have been trained to learn that those two things are similar. The vision encoder would have been trained to create representations similar to that text. So the decoder received the same two things from text and image.
And there was another question from DJ.
Yeah, hi. I see a very intense conversation is happening right now, and I don't want to add more complexities to it. I have a simple question. In my professional capacity, I do build RAG solutions, and I always looking for more innovative ways of incorporating those RAG solutions, and this is the reason I'm participating in this meeting. I see that a person asked how the plot or graph data could be trained, or how could we retrieve useful insights out of it. So in my experience, I've used something called GPT-4 Vision, and that's able to extract the meaning out of the plots and graphs. Like I can ask and it will tell me what exactly that graph exhibits or what exactly that out of that graph. So my question to you, is that something we can do using, sorry, what was the model name? ColPali?
Yeah. I'm not entirely sure. I don't have that much experience with that, so maybe Ben can answer it.
Sure. GPT-4 Vision or GPT-4o Vision language models, given an image and a question, they can reply based on the image. A ColPali or a clip model is a retrieval model. So in our RAG setup, as I'm sure, let's say we've got 1,000 images. I ask my RAG setup, where's the car park at the company? The retrieval part of the RAG will use clip, get images of maps from the company, and then it will give that to GPT-4 Vision or any vision language model, and it will ask that model to answer the query. So that's the difference between those models.
The distinction I'm trying to make is that I'm not trying to search the image. I'm not asking where is the cat eating carrots in the picture. I'm not looking for an image of a cat eating carrots. What I'm trying to find is, give me the top 5 countries given the plot or graphical data that it represents. So would it be able to answer those kind of questions?
A vision language model,
Mhm.
yes. If the information was in the image, of course.
And I think maybe at the moment, the open source alternatives like the vision language models from frontier providers like Google or OpenAI aren't that advanced yet, or at least less advanced than like the competitors. But what you saw like with normal LLMs or language models was that initially, like you had GPT-4 or the ChatGPT coming out, none of the open source alternatives could actually meet the standards. And over the course of one and a half year, you've seen that each one of the like open source model providers has actually gained in terms of across the benchmarks. And that's something we'll see with vision language models over the course of time. Maybe at the moment they're less advanced or less capable, less higher scoring on benchmarks, but they are an alternative that you can use privately. You can self-host, you can actually do with whatever you want without sending your data to OpenAI or any of the other frontier vision language model providers.
And there's one thing I just add there before we close, is that within a RAG setup, retrieval is often the most impactful part. Even best language model, if you're not giving the right documents to that language model, it can't answer the question. And as well as having that impact, retrieval is more straightforward to fine tune, and you can typically fine tune because it's easier to create data that represents that task. So you can actually significantly boost your RAG setup by optimizing the retriever. And just because you use an open source retriever doesn't mean you need to use an open source LLM. So you could set up, like, let's say, a clip retriever, then go and call OpenAI's GPT-4 because it's really good. So there's no reason why you can't combine the two, because there is a significant difference between the compute that it requires to serve clip and even Qwen VL or any of these open source models can compute. So you can combine them. And the last quick thing I'll answer is Vikash's question about how ColPali is different from keyword extraction, OCR, document parsing. I would definitely take a look at that paper I was playing with in the notebook called OCR 2.0. That paper goes into the shortcomings of current OCR practices and how we use them with LLMs. We chop up and mutate all these documents and then throw them into an LLM, and the LLM doesn't have any of the concept of space or the layout of the page or a plot or a diagram or any of these things. And what they're starting to call OCR 2.0, which is just a vision language model trained for document tasks, is that model understands a plot. It will understand an X and Y axis. It can see that two things are next to each other on the page, this kind of information. So I'll definitely take a look at that paper.
Thank you, Ben. Thank you.
Cool. Thanks for the questions, everyone, and thanks for joining. The notebooks are available on the Google Drive. They will be added to the YouTube video that I'll upload in a couple of days. If any other questions or follow-ups, feel free to contact us on social media or on the Hugging Face Discord. We're happy to help you with setting up your use case. We hope to see you in a couple of weeks. Ben, thanks for your notebooks.
Thank you very
See you,
much.
everyone.